I'd like to look at some properties of semiconductors. Semiconductors are elements like silicon. They're neither metals nor nonmetals. They have some rather unique characteristics. For example, with metals, when metals get hot, their resistance increases. Semiconductors are different. Here I have a piece of silicon in a thermistor. It has 1.2 kiloohms at room temperature. As I heat it up with a hot air gun, you can see the resistance is dropping. Very different than metals. Also, the resistance changes quite a bit. The objective here is to talk about what is the resistance of intrinsic silicon, that's pure silicon without any impurities. Explain what the different type of materials are. As I add impurities, such as phosphorus or boron, I can create very different types of materials called N-type and P-type. And then we'd like to determine the resistance of some doped silicon. Now, silicon is element number 14. It's in column 4 of the periodic chart. As such, it has 4 electrons in its outer shell. When forming a crystal, silicon will form covalent bonds with 4 neighbors, resulting in all of the electrons tied up in covalent bonds. What that means is that there are no electrons available for carrying current at 0 degrees Kelvin. Once you get above 0 degrees Kelvin, there's a chance that some of the electrons will jump out of the covalent bonds due to thermal energy. For example, here, if an electron gets out of its covalent bond, it's free to roam throughout the crystal. What happens then is the electron has no place to go. All the covalent bonds are filled. The electron can carry current. In addition, I create a hole, meaning a missing electron in the covalent bond. What can happen once I create a hole is a neighboring electron could jump out of its covalent bond and fill that hole. The result, however, is I now have a missing electron or hole to the right. A little while later, another electron can jump out of its covalent bond and fill that hole, creating another hole to the right. The net result is it looks like I've got holes flowing to the right. I could treat holes as a type of charge carrier. So I have holes to carry charge as well as electrons. Now, a property that silicon has is the number of holes times number of electrons, called N and P. The product is constant. The way that works is, suppose I have a large number of holes in a piece of silicon. If an electron is created, it will immediately fall into an open covalent bond, namely a hole, and disappear. Conversely, if there's a large number of electrons in a piece of silicon, any holes that are created will quickly be filled by an electron. Likewise, you get number of holes times number of electrons are constant. If I have more holes, that means I have fewer electrons. In addition, the number of holes, number of electrons are related to temperature. What that means is as temperature goes up, I get more and more charge carriers. The silicon that looked like an insulator at 0 degrees Kelvin eventually starts behaving like a conductor. At room temperature, the number of electrons times the number of holes is the intrinsic carrier concentration, is 1.5 times 10 to the 10th. There's also a thing called mobility. Electrons can travel throughout a crystal more easily than holes. The holes actually are missing electrons that get filled by other electrons, looking like a positive charge particle moving throughout the crystal. So it's not surprising that it's a little bit harder for holes to move than electrons. The resistance of a material is a function of the mobility. To find the resistance, it's actually easier to find the inverse of the resistance, called the conductivity. Conductivity is a function of the number of charge carriers. For semiconductors, it's both electrons and holes. If, for example, I have a piece of intrinsic silicon, meaning pure silicon at room temperature, 300 degrees Kelvin, the conductivity would be 4 times 10 to the minus 6, 1 over ohm centimeters, or for units that we're more familiar with, the resistivity would be 231,000 ohm centimeters. That makes silicon a poor conductor at room temperature. However, I can change the number of charge carriers by doping it. Suppose I were to dope the silicon with boron at 10 to the 16th atoms per cubic centimeter. That may sound like a lot, but you have to remember Avogadro's number is 10 to the 23rd atoms per cubic centimeter. At 10 to the 16th atoms, I only have 1 out of 10 to the 7th atoms being an impurity. The silicon crystal still behaves like a pure crystal piece of silicon. However, by doping the silicon with boron at 10 to the 16th atoms per cubic centimeter, I've created a large number of holes. Boron only has 3 electrons in its outer shell. The crystal needs 4. The 3 electrons in the boron atom fill the covalent bonds of the crystal with the silicon atom that it replaced. However, that 4th electron is missing, creating a hole. As a result, the hole density in the doped crystal will be roughly 10 to the 16th atoms per cubic centimeter. The number of electrons, on the other hand, since the number of holes times the number of electrons are constant, will be much, much less. Rather than being 10 to the 16th atoms per cubic centimeter, it's down at 10 to the 5th. Likewise, I have 10 to the 11th more holes than electrons. Almost all the charge carriers are holes. The resistance of the same piece of silicon that we looked at, resistivity drops down to 1.25 ohm centimeters, 184,000 times smaller than the undoped silicon. I can take a piece of silicon and turn it into a conductor by doping it. I can also build a resistor. For example, if I built an O402 resistor, which has dimensions of 0.1 by 0.05 centimeters, I would have a 50 ohm resistor. I can also dope silicon with phosphorus. Phosphorus has 5 electrons in its outer shell. 4 of the electrons fill the covalent bonds. That 5th electron has no place to go. It's free to roam throughout the crystal, making an N-type material. If I dope the silicon with 10 to the 16th atoms of phosphorus per cubic centimeter, I'll have 10 to the 16th electrons per cubic centimeter roughly 10 to the 11th times bigger than the number of holes in the crystal. Likewise, almost all the charge carriers will be electrons. It behaves like an N-type material. Again, using the same calculations as before, if I dope the silicon with 10 to the 16th atoms of phosphorus per cubic centimeter, the resistivity drops to 0.481, and the resistance is 19.2 ohms. If you recall, for p-type material, the resistance was 50 ohms. N-type material with the same doping was 19 ohms. N-type material has slightly less resistance than p-type material. That doesn't really matter, however, because you can adjust for that just by changing the doping concentrations. So here's the problem. Suppose I want to design a resistor that's 1,000 ohms. I want the resistor to be O402 resistor, meaning I've got a piece of silicon that's 0.1 centimeter in length, 0.05 centimeters in cross-section. Find the doping that creates a 1,000 ohm resistor. To do that, I would first find the resistivity that I need. Resistivity is 25 ohm centimeters. Inverting it gives you 0.04 ohm centimeters conductivity. From that, I can find the number of phosphorus atoms per cubic centimeter I need in the doping. If I dope an O402 resistor with that much concentration of phosphorus, I'll get a 1 kilo ohm resistor. Likewise, resistors are actually very easy to make out of silicon. I can also make temperature-sensitive resistors. Suppose, for example, I doped 2 sides of a piece of silicon very heavily, creating an N-type material. In the middle, I left this intrinsic. I'll have a fairly high resistance for intrinsic silicon. If I make it thin enough, I can make the net result 1,000 ohms. For example, if I make that thickness 11 microns, the resistance will be 1,000 ohms at room temperature. Now, if I move away from room temperature, the resistance changes. As the temperature goes up, the number of thermal electrons increases from this equation, and I wind up with a lower resistance as temperature goes up. As temperature drops, the resistance goes up. Likewise, silicon behaves very differently than metals. For metals, resistance goes up with temperature. For semiconductors, it actually goes down. This again is what we saw in this video at the beginning. Take a piece of silicon and start heating up with a heat gun. At room temperature is 1.2 kiloohms. As it gets hotter and hotter, the resistance drops. And again, notice the resistance drop is actually fairly dramatic. Went from 1.2 kiloohms fairly quickly down to 600 ohms, 500 ohms. I have a very easy way to measure temperature using semiconductors.